there. So we'll go ahead and get started. Everybody can hear me okay? Yeah? All right. So I'm a little bit worried because I looked at, we only have like 4 lectures left, and we are only just now starting chemistry. I really don't know how much of chapter 10 or 11 we'll get to. Whatever we don't get to, oh well. It's about teaching ourselves to be good scientists, not to memorize a bunch of stuff. So also you've seen exam 3 hopefully posted on the content page of Learning Suite. Please let me know if you have any questions or concerns about that. And we'll just dive right into the chemistry. So the first little bit of chapter 10 spends a lot of time talking about addition chemistry to alkenes and alkynes. And a lot of this is a review from undergrad organic chemistry. So I don't want to duplicate a lot of that, but there are some nuances that you may not have appreciated. So let's just begin with acid catalyzed hydration of alkenes. So just take this alkene as an example, and then we'll use hydronium as our acid. The slow step is protonation of the alkene. And so in the end, we're going to regenerate our acid. So we would call this a general acid catalysis, because the proton transfer is occurring during the rate determining step. You get a high energy carbocationic intermediate, which then water adds to quickly to give the oxonium ion, which is then deprotonated in a fast step. Also, water can leave from the oxonium ion. And so these last steps are reversible, but in the end, we're going to remove the proton. I haven't shown you that proton transfer step, and I won't. In the end, you regenerate your acid catalyst and get your alcohol. In terms of the kinetics, the reaction's first order in acid and first order in alkene, as you would expect, based on what I've identified as the slow step. There's a primary kinetic isotope effect for the acid, for the proton donating species of the acid. So we'll just say primary kinetic isotope effect there, which is consistent with that proton changing its bonding. Other important details, of course, regioselectivity follows this Markovnikov pattern, which we probably don't need to talk about. The reaction's regioselective for the more stable carbocation, and that explains where the alcohol goes. A couple of interesting features that give you a sense for why the intermediate here is likely a carbocation instead of a alternative bridging species. I don't know if you remember when we talked in the MO chapter about ethylene cation, and if you were to add a proton to ethylene, you don't get this, but instead you get a weird 2 electron 3 center bond, where you've got this bridging hydrogen. And you might imagine that such a thing was occurring here instead of a discrete carbocationic intermediate. Here's the proton we added. So, but there's evidence against that, and the evidence is as follows. If you go from propene to trans or even cis butene, the rates of addition of water, the rates of hydration, are similar. Now, if there were a bridged intermediate, you would predict that substitution on either side, if there was a bridged carbonium ion, you would predict that addition of substituents on either side would stabilize the intermediate and enhance the rate of the reaction. But instead, as long as one side is monosubstituted, the other side can be monosubstituted as well, and there's really no rate acceleration. When you start adding additional substituents, that's when the rate acceleration occurs. So this species is faster than the trans and cis butenes, and then the tetrasubstituted alkene is even faster. So what that suggests is that you have a discrete carbenium ion rather than a bridged carbonium ion. Your text mentions alkynes. There's maybe some stuff to consider there, but I won't talk about them right now. Any questions? Anything you want to talk about for alkene hydration? I should point out that we mostly talk about this to illustrate some reactivity principles. This is not a synthetically useful reaction, in part because your molecule has to be really, really simple because you require very strong acids. And of course, there are a lot of interesting functional groups that are not tolerant of very strong acids. So in practice, hydroboration is a better approach and is more often used in converting alkenes to alcohols. So if it's okay, unless there's anything else you want to say, we can talk about addition of hydrogen halides to alkenes. And much of what we say about alkenes will be true for alkynes as well. As you would expect, the standard mechanism that you were taught in undergrad organic is that, again, it's just exactly like alkene hydration. You've got a discrete intermediate that is the carbocation, which then the chloride nucleophile adds to. And that's simple, but it probably is overly simplistic because as you start to change the structure of the alkene, some interesting things can happen. So in terms of regioselectivity, we observe Markovnikov patterns. That's not apparent from this example, but we can make it we can make it so by editing the example just a little bit. Did I break it? No. There we go. So though there are some mechanistic complexities that are useful to think about. So let me show you a particular example of this that ends up being kind of confusing. Often for these kinds of reactions, you use a decently polar solvent as but you don't want it to compete with chloride in the second step. But in practice, you often see such competition products. So if you react this particular olefin, you observe the following products. And I'll show you product ratios as well. All right, so it's sort of a 2 to 2 to 1 product. So tell me a little bit about where each of these products come from. How about the alkyl chloride here? Where does that come from? Chime in, anybody? That's okay. Okay. Okay, good. Standard approach. How about this one over here then? Where acetate is. Okay, I suppose, yeah. I mean, you could think about acetate coming in and doing the nucleophilic substitution there. I will tell you, though, that this is acetic acid, and so though acetate is a good nucleophile, the protonated version isn't, and so it would be unlikely to do the SN2. Can you think of another intermediate that might be more reactive with respect to acetic acid? Yes. Yeah, exactly. Yeah, so acetic acid could intercept that carbocation. So this is sort of the competition product. How about the one in the middle? Where do you get that from? The evil methyl rearrangement, which would involve one of these methyls leaning over through a bridged sort of carbonium, either intermediate or transition states, difficult to say, to get you this carbocation. Now, an interesting piece of evidence here in terms of the kinetics of this reaction, it is first order in alkene, as you would expect, and first order in acid. So that suggests rate determining protonation of the alkene. That's the slow step. In agreement with that, there is a kinetic isotope effect for HCl versus DCl. The KH over KD is small, but it does suggest some amount of proton transfer in the rate determining step. However, so all of that's as we expect. One interesting thing, though, is that if you add, in this case, if you add additional chloride salts in the form of Cl minus, the product ratio here for this specific example doesn't change. And that should maybe be troubling to you. Why? Other than a vague sense of foreboding. Go ahead. That's right. If indeed your intermediate really looks like this, a carbocation, it would seem that that adding chloride could outcompete the acetate. And another thing is that why don't we see any acetate substitution in the rearranged product? Why is that mostly chloride? And to rationalize that, you have to invoke something that actually happens a lot in organic solvent, but that we don't often think about, and that is ion pairing. So again, protonation of the alkene is slow, but what you have immediately after protonation of the alkene is not a free and breezy naked carbocation. You have a contact ion pair, and it is surrounded by a solvent cage. And it turns out that diffusion of Cl minus into the bulk solvent is slow. So it turns out that the 1-2 shift is quite fast within the contact ion pair. And so then Cl minus can hop right on there without any interference from acetate. And the unrearranged product probably comes from immediate recombination of Cl minus, immediate attack of Cl minus on that carbocation in the contact pair. It's only at some point that acetate, in order for acetate to compete, acetate would have to diffuse in and chloride would have to diffuse away. Okay. So it seems like adding acetate to that carbocation necessarily requires the contact ion pair to be disrupted. So because diffusion of the chloride is slow, even if you add chloride to the solvent to try to bias the reaction in one way or another, this chloride in the contact ion pair is never in equilibrium with chloride in the bulk solvent. So basically, this is all the chloride you have for this reaction in the contact ion pair. It will either attack immediately, or rearrangement can occur and it will attack, and then there'll be a small amount of situations in which chloride escapes the ion pair and acetate, which is the solvent from the solvent cage, can attack. Questions there? Sure, Austin, go ahead. I don't know. That's a good question, and you would think maybe that the more stable carbocation would have a longer lifetime, and that maybe that would make it easier for acetate to react with. I don't know why that's not observed. It's possible it does form, but in a pretty small amount, and what that might reflect is the relative rate for the methyl shift versus just immediate recombination of chloride in the contact ion pair. In this case, acetate is solvent, so the fact that acetate doesn't outcompete the chloride is kind of an impressive observation, because the solvent cage would be sort of acetate molecules surrounding it. So I don't know why we don't observe any there. It could be we don't because it's too small to detect, because the rearrangement isn't that fast. I don't know. Other questions? But this, so you need to be aware of the possibility for contact ion pairs with carbocations, but it's not universal. And if you did cyclohexene as an example, you can outcompete acetate in the case of adding HCl to cyclohexene. So there's a large dependence on the structure of the alkene, and you have to be prepared for multiple mechanistic possibilities. There's some interesting things to say about stereochemistry here, things that I learned from this text that I didn't necessarily know or appreciate based on what I'd been teaching in undergraduate organic. If you take this isotopically labeled cyclohexene, which allows you to see some stereochemical issues, and if you subject it to reaction with HCl and acetic acid, You can observe the products that come from syn addition of HCl across the double bond. I'm not sure why these other deuteria are there. Oh, wrong. So you've got the syn addition product. You have an anti-addition product. Oh, Joshua, we're struggling today. This is the anti-addition product. And there is another anti-addition product that can occur if the H from HCl adds first over here. Oh, hold on. We actually, for this, for the product where HCl, where the hydrogen adds first to this carbon, we actually can't tell whether this is syn or anti, right? Because what you had on that carbon to begin with is a hydrogen, and then you added another hydrogen there. The hydrogens aren't labeled. You can't tell which is which. Does that sort of make sense? But then there's also sort of the copy of this anti-addition product that is from, acetate competition with chloride for the carbocationic intermediate. And of course, to the extent that these are chiral, you've got racemic mixtures of enantiomers. You can't favor one enantiomer over the other. But there's some weird kinetic observations. The syn product that I've noted here is second order, first in alkene and first in acid, and that's exactly as expected. Though in order to explain the syn stereochemistry, you have to invoke a transition state that would look something like this. And I'm just going to be sort of general. Those aren't methyl groups, those are just connections. Probably you have to invoke a transition state that looks something like this, where, you're forming the hydrogen carbon bond at the same first, but at the same time you're sort of breaking the hydrogen chloride bond and starting to form a new carbon chloride bond. So this would be as though it would be hard to distinguish the mechanism of this reaction as concerted versus stepwise. It wouldn't necessarily be clear whether we have a carbocationic intermediate here. It could be that the addition is concerted, that is, the pi bond attacks at this point while the hydrogen chloride bond attacks there. Alternatively, you could imagine a situation where you do have a carbocationic intermediate, but it's a contact ion pair, and the chloride reacts very fast along the same face before it has time to swim around and come around from the other side. Alternatively, the anti-addition product actually shows third order kinetics. That's bizarre. And what this suggests is the anti-addition product does not come from a naked carbocation where chloride has the ability to swim around and come in from top or bottom, which is what I said in 351. The reality is more complicated. The reaction is first order in alkene, also first order in HCl, and then, interestingly, first order in Cl-. So what happens there, likely the relevant transition state there, is an alkene where you're starting to form a bond with HCl on one side at the same time as you're starting to form a new bond with chloride on the other side. And this is a proposed termolecular transition state. And you may remember that those are supposed to be really rare because termolecular collisions almost never happen. It's statistically hard enough to get a binary bimolecular collision, but to have three things come together simultaneously, that's really hard. And so what it likely is collision of the alkene nucleophile with HCl, and then to create a weak complex, and then you get in another step a bimolecular collision of that complex with chloride. I won't draw the transition state for the anti-addition product of acetate, but it's also termolecular, and so it resembles the transition state I've drawn that I've drawn up here. Yeah, go ahead. Our termolecular reaction is very slow because it's hard to get all three molecules to align. I guess I would say this has got to be slower than a typical just bimolecular reaction, but it's not. I think we'll call this a formally termolecular transition state, in the sense that there are three molecules in it, but likely getting to that transition state is stepwise. That is, one molecule of HCl encounters one molecule of alkene. Reaction doesn't happen yet. That complex is weak and has a long lifetime. And then a third molecule, the second molecule of the chloride ion, then encounters that complex in a more or less bimolecular, second bimolecular collision. Is that sort of understanding? Taking molecule 1 and molecule 2, making a complex, and then they're finding molecule 3. So we don't have to have 1, 2, and 3 find each other all at once. That's right, and that's why what likely happens is 1 and 2 find each other, and then they find 3 together. Yep. All right. So that's just to demonstrate that the reality is more complicated than perhaps you expect or might have appreciated. And such formally termolecular transition states also are observed for addition of HCl to alkynes. We won't talk about that, but there's some detail about that in your text. Okay, anything else we want to say about how do you observe this? Or, I'm sorry, is that your question, Mario? Or how do you actually observe this? Okay. I think the evidence for this is there's two things. One, it's the stereochemistry of the product where the H and the Cl are anti to each other. And then second, though you could get that randomly, right, if chloride swam away and then just happened to come in from the bottom face of the carbocation, the real evidence that suggests it has to be a transition state that involves three things is the observation that appearance of this anti-product has third-order kinetics, and it depends on concentration of alkene, HCl, and added chloride. In other words, they observed if you add Cl-, you can speed up the observation of this anti-product. Okay, good. Other questions or concerns? All right. Well, since we're in the business today of pulling back the curtain and showing you how complicated the world actually is, you can feel grateful that we oversimplified to you in undergrad organic, but we're going to do the same thing now for electrophilic addition of halogens to alkenes. So the classic example of this is bromination, where you've been taught that pi electrons attack the bromine sigma star at the same time as lone pairs on the bromine are attacking the other carbon of the olefin at the same time as the bromine-bromine bond is breaking. And you get you get the bridged halonium ion as an intermediate. Those carbon-bromine bonds are quite long. This is called a sigma complex because you actually form sigma bonds between the carbons and the bromine. It is called a halonium ion. We don't see carbenium ion, and the evidence for that is we see exclusively, or predominantly rather, anti-addition of Br2 across the double bond, because the second the Br minus comes in from the backside and opens up in sort of SN2 fashion and opens up the bromonium ion. Your product is a so-called vicinal dibromide, and alkynes can do this as well. If you have a second equivalent of Br2, you can get tetrahalogenated alkynes. Interestingly, this is something I didn't know. The reaction can be done with fluorine, though it's highly exothermic because of the strong strength of the new carbon fluoride bonds relative to the pi bond and the fluorine-fluorine bond. So exothermic that it is explosive at 25 C. So nobody does it. You can do it at low temperatures, and there are examples of that. Cl2 is exothermic by minus 44 kcals per mole. Br2 is exothermic by minus 29 kcals per mole. I2 is thermoneutral and therefore reversible. So there are examples of iodination of alkenes, but it's not, I think, as downhill in energy as it is with bromine or chlorine. Go ahead. For H2, so you can look that. I don't know what it is, but you can look that up in heats of hydrogenation for alkenes, actually. That'll tell you exactly what that number is. All right, so yep, you get, there's a stereochemical preference for anti-addition. I don't know that we need to say any more about that. The reaction is first order in alkene, and it's also first order in Br2. There's evidence that both carbons are involved in a couple of different ways. First, if you do that sort of same reactivity series where you start to add substituents first on one side, then on either side. The rate is faster for propene than it is for ethylene, faster still for trans-2-butene. If there were a carbenium ion intermediate, there wouldn't be, as we observed previously, the rates of addition to the propene and the trans-2-butene would be similar, right? Because both of them involve a carbocation that's similarly stabilized. That's sort of what we saw here. But instead, because both carbons are involved in the rate determining step, you see an acceleration of rate as you start to add substituents on either side of the alkene. And the numbers are available in your text. We don't need to talk about them here. Another piece of evidence that suggests that both carbons are involved is if you do the kinetic isotope experiment, and for reasons that I'm not sure, your book talks about how this experiment was done with per-deuterocyclohexene, but they know that the kinetic isotope effect is due to these two carbons, the ones involved in the olefin. KH over KD is actually 0.53. This is a large inverse secondary kinetic isotope effect. We see inverse secondary kinetic isotope effects when we're going from sp2 to sp3 hybridization. Typical size for a secondary kinetic isotope effect of this kind is around 0.8. So this is bigger than that, and that's rationalized by the fact that you have two carbons undergoing that rehybridization in the transition state. All right, any questions you want to ask there? So can I explain it off the top of my head? No. Do you remember that vibration, a particular vibration for an sp2 hybridized carbon is different than for an sp3 hybridized carbon? I believe it was more loose for the sp2 than for the sp3. And so go back and look at your notes. That's a cop-out, isn't it? And fine, Dakota, I'll go look it up. I'm not actually irritated, so don't worry. I'm going to, let's see, share my screen again. Can you now see my whole screen instead of just the iPad? All right, there we go. So these are my notes from our kinetic isotope effect chapter, and this is why your exams are open book, because it's hard to keep this stuff straight, and you'll have to go back and look this up a gazillion times before you remember it. So we said when going from sp3 to sp2, you want to talk about force constant changes. We mentioned that for sp3, the out-of-plane bend is sort of stiff. The out-of-plane bend for sp2 hybridized carbons is weaker, has a weaker force constant. So a large change in the force constant from going from sp3 to sp2 means a decent sized change in 0-point energy. And we rationalized that by saying that, let's see, the 0-point energy difference reflects the large force constant in the sp3 hybridized carbon in the ground state. If in the transition state you resemble sp2, that force constant is smaller, which means the 0-point energy difference should be smaller as well. So You see a normal secondary kinetic isotope effect when going from sp3 to sp2. You see an inverse secondary isotope effect when going the other way from sp2 to sp3. I realize that's probably fast. That's a quick review. And again, that's something that you'll have to go back and convince yourself of, as I just had to do. I'm only partially convinced, so there's clearly a lot I need to learn. Other questions? As expected and as you know, we can intercept the polonium ion intermediate with other nucleophiles. Your text mentions that, and I won't talk about it further. Another thing your text points out is if you put some group attached to the olefin that could stabilize a positive charge by resonance, then you actually do see a carbenium intermediate with a positive charge on the carbon adjacent to the stabilizing group. An example of that, I won't draw the whole thing, but if you wanted to do this olefin as a starting material, you will see products that are consistent with anti-addition as the major product, I think 73%. But then you'll also see a fair amount of product from syn addition across the double bond. And they explain that by invoking an actual discrete carbocation intermediate stabilized by the benzene ring. What else do I want to say about this reaction? There is evidence for a contribution of single electron transfer. So if you watch the UV vis as this reaction is happening, you see a transient band that disappears as the bromonium ion forms. And this is kind of bizarre. I mean, we've looked at bromonium ion formation as though it were concerted, but spectroscopically you can observe the following. It's very weird, and do you have to memorize it? No, but it's kind of interesting, so we'll talk about it. There appears to be some sort of fast association of Br2 with the alkene in kind of a pi complex where there's a partial positive on the alkene and a partial negative on the bromine. And it turns out that thinking about that is actually just a resonance structure of thinking about full-on single electron transfer of an electron from the alkene to the bromine. So this is what we call a charge transfer complex. And then slower sort of, I guess, recombination of the radicals to give you the bridged polonium ion intermediate. Now, I don't actually know. It's possible that UV vis is exciting this kind of thing. So it's possible this means that the charge transfer complex isn't what's occurring in the mechanism, though it's also possible that it is. And so that's a level of complexity that you probably didn't want to know about. Another level of complexity is for some olefin starting materials, there's evidence for 1 to 3 bromines involved in the reaction. So as an example, sometimes reactions are second order in Br2. We're not going to rationalize when this occurs and with what substrates. This is more of being prepared for the possibility of these things happening. I'm not claiming that this substrate has been observed to undergo this kind of reaction, but there is evidence for needing a second molecule of bromine to facilitate formation of the bromonium ion. Now you're going to say stop because this is horrible, and another reason you may say stop because this is horrible is I appear to have broken the octet rule. Right? There were 3 lone pairs on that bromine. I drew an arrow and I didn't break a bond. And I'm going to say mwahahahaha, or I can actually do that better. Bromine, by virtue of its large size, can form hypervalent, can bond in hypervalent arrangements. And it's actually thought that it's this BR3 species in the second step that delivers the other equivalent of bromide. And so the kinetics for these kinds of things can be incredibly complicated. As an example, there's a component that is only first order in bromine. At the same time, there's second order in bromine reactions going on. And at the same time, you've got a contribution from the Br3 minus anion, and it's overall first order in alkene. I wouldn't expect you to derive that kind of rate law, but it's just messy. And so, again, the world is not as simple as you thought it was. For chlorination, you often see evidence for radical pathways. So people tend to do bromination more than chlorination because they want to control the reaction. There are some other details in this section, but I don't think they're necessarily relevant for us. Anything you want to ask there? In that horrific mess of details? Kim, you look depressed. So stop me. What are the questions? Okay. I think there's a lot we could say about hydroboration. I feel like this is one that you should know pretty well. It is in your text, so I feel like we don't need to say too much. The one thing that there's a couple of things we should add as complicating details, and that is that BH3 exists predominantly as a dimer. We talked about this or looked at it maybe in the chapter on chapter 14 where we were doing MO calculations. It can dissociate to form BH3 monomer. Often, though, if your solvent is an ether, which is frequently the solvent used for these kinds of things, you form a Lewis acid-Lewis base complex between boron and the ether oxygen. We can call this BH3.THF. It's Lewis acid-Lewis base reaction. For many hydroboration reactions, they can actually be zero order in alkene because dissociation of either the BH3-THF complex or the BH3 dimer is slow enough that that's rate determining. And so because of that, a lot of alkenes react at similar rates, and the alkene doesn't make a huge amount of difference. It's thought that the reaction once you do have BH3, it's thought that you first form what's called a pi complex, where you sort of have the empty p orbital of boron sitting down on the pi bond of the olefin to form sort of another one of these three-centered two-electron bonds. And then that, and you know how to push arrows for hydroboration, oxidation, hydroboration. So I'll just show you the syn addition product. But it's thought that you take the electrons from the olefin and form a full bond here at the same time as you're delivering the hydride. You see anti-Markovnikov selectivity here. And that's typically thought of just because of sterics. So as an example, if you use this alkene, you'll get the proton here and the BH2 here. Though there is also an electronic component that you can rationalize if you tell yourself that the formation of the carbon-boron bond precedes the formation of the carbon-hydrogen bond, and therefore the hydride is delivered to the carbon that can more readily bear the positive charge. Okay, anything we need to say there? Okay, well that's it for today. So there's still a ton in Chapter 10. What I'm going to try to do is pick and choose the most important things in both Chapters 10 and 11, and we'll continue on from there. If you have any questions immediately, I'm happy to stick around for a few minutes, but we'll go ahead and stop the recording.